share. You're able to see?
Yes, I'm able to see.
So for deep learning, I have written a few articles like deep learning, right? So types of artificial neural networks and their applications. So one is so there are these supervised neural networks, simple artificial neural network used for regression and classification. Then there is convolutional neural networks used for computer vision, recurrent neural networks used for time series analysis and natural language processing. Then there are unsupervised neural networks also, like self-organizing maps, deep Boltzmann machines, and autoencoders. But this is like a very high level view of what you might see in the future if you start a journey with neural networks. But there are a couple of things that you should be aware of, like there is this paper, backpropagation paper by this fellow Leekan Yan, and it explains backpropagation very clearly. And if you want, I can explain that too. But a couple of things that you should be aware of is this activation. Oh, sorry. Couple of things that you should be aware of is this, that this activation functions. So threshold function is also called the step function. Why we are doing this? This is going to form the basis on which you would. So if there is any lag in audio, you can let me know. But this is so this is we'd start with, there is a concept of activation function in neural networks. What I'll show you is that in Paint, neural networks, what is, so in, you are familiar with biological neural networks, right? That it consists of cells called neurons.
Cells, yes, cells, neurons and all, yes, I'm aware of.
So
we have read through that also in one mail. Yeah, not mail, sorry, book.
Okay, so let's assume that this is a neural network, and there is a input to it. Okay, now, and there is an output from it. But let's say that input is x, and if this over here we would write sigmoid activation function. Activation function. Then what would this become? Output become? Your output would become, this is what happens inside of a cell, 1 upon 1 plus e to the power minus x. Okay, so this is a neuron, essentially speaking. And if you remember from logistic regression, this is a neuron. Concept of neuron and machine learning. Okay, now do you remember logistic regression? Abhijit?
Yes, I know that. Yeah, I remember it. Yeah.
So if you remember it clearly, then you might be thinking that 1 second, let me save it. Desktop 1. If you remember logistic regression, I'd open the slides as well. That what we are doing over here is what we did in logistic regression. So logistic regression is essentially in the single cell, right? The single cell. If you remember, look, doesn't this look similar? Sigmoid. This is instead of x, this is x minus mu over s.
Mm-hmm.
This is
Yes,
logistic.
yes.
So this is logistic.
Logistic regression only. It looks like it was
Yeah, so it looks like real logistic regression only, and it is logistic regression, effectively speaking. Logistic regression, what you see over here in this cell is, I put it over here. This is the logistic function, and what you are seeing over here is that a value x is passed to a function which is converted into a weight multiplied by a weight vector beta of betas, and your input vector x, then that is passed as the exponent to the to the Euler's constant, negative to the Euler's constant. So this is basically, this forms the basis of neural network. Now, if we open these slides, if I'd open the slides, when to one second, let me see if there is anything else left. Deep sparse steps involved in training in, what is this? That's cool. So this is about convolutional neural networks. You don't need to get into that. Basically, deep learning neural networks forms the basis of deep learning, and basics of neural networks comes from logistic regression. And you need to remember two functions. One is sigmoid and one is logistic. And we have seen that over here in control tab over here. So we were over here, right? I told you that we have sigmoid function. So instead of sigmoid or logistic function, you can use some other functions also. So this question is asked in interviews a lot of times, like explain the kind of activation functions you can use, and what is the advantage and disadvantage of using them. So this is threshold function, which is 0 before negative values of x, and it is 1 for the positive value of x, like as shown over here. So can I the problem with this function is that this is not differentiable. So even though it is not differentiable, it is still used in building neural networks. And theoretically speaking, it is hard to work with it, too hard to do the math with it, to explain it to in layman language. Then there is rectifier function, which is ReLU, also called as ReLU function, which is 0 before x is equal to 0, and then it is equal to the value of whatever is being passed to it. So this is not differentiable again because of this sharp point over here. This is not differentiable at x equal to 0. Before and after it is differentiable. This sigmoid function you are familiar, and we also see this in logistic regression where logistic function is used. I'd put the logistic regression also over here. Just give me a second. Logistic function. Logistic function. function is there, then there is hyperbolic tangent. Hyperbolic. So the difference between sigmoid
What
function
is the
and
difference between rectifier and the sigmoid? These are different types of curves, right? For normal distribution.
activation. No. Sorry, didn't get the question. Could you come back with the question again?
Yeah. Means what is the different activation functions? What is the significance of these different functions?
The significance of these different functions is that the significance of these different functions is that they are used at times to convert when you have a value. Let's say that you get you have a vector. I'd open a new function. Let's say you have this vector called weights. Okay, weights. W naught is there, W1 is there, W2 is there. Okay, let's say, and you have input vector x, and this is equal to x naught. This is by definition, we assume it to be equal to 1. Then there is x1 and there is x2. So in a linear combination of these weight vector and x vector is W transpose x. W transpose x meaning what you have is W naught x naught plus W1 x1 plus W2 x2. Now, when you are doing a prediction or classification of a binary variable 0 that is expected to give you 0 and 1, what do you think, how would you proceed with this? If this is the value, let's say you have some values over here, x1 and x2, and you only want 1 and 0 only. Now, when you want, if these weight vectors have some values, like this is a real is all of these are real numbers, and all of these are real numbers as well. So this is not this this expression may or may not be equal to 0 or 1. If you agree with me, may or may not be equal to 0 or 1.
Yeah, it may or may not be. Yes. Based on the values of the vectors, weight and the.
Yeah. So to
it
make
may
them
be 0.
yes, to make them equal to 0 or 1, to it just get a. So let's say if you have this step function, step function or threshold function only, you can easily convert. If you have I'd go to the paint again and show you that. Let's say you have a circle over here like this, and this is we have 3 x's. So 1, 2, and 3. So x1, right? x2 and x3. Now what happens over here is you have weight vectors over here. Weights are multiplied by these x's.
X is your numbers, right?
Yeah, 1 second, I made a mistake. This is not 3. This is not 3. This is not 2. And this is not 1. So I'd write them again. This is 0, this is 1, and this is 2. Okay. So when you pass them through this, you get something of this sort, WTX. So I draw the line here. What happens in this function is that if you expand it, so this is W transpose X. Okay. Now if you
Mhm.
pass it through the sigmoid function e to the power minus x, then what would happen? What does sigmoid function do to values when you pass it to it? Will so the what will happen if you pass it to a sigmoid function like this? If you look at the curve of it, if you give it the value of 0, if you give it the value of 0, if x is equal to 0, like over here it is not saying that, at x equals to 0 the probability is half. So I'd scroll out again and tell you,
X0 means probability is half, is it?
yeah, so we will have to get a table at x. So there is, even though it is continuous, when x equals to 0, let's say we call this as p of wt and x. So when at x equals to 0, this is equal to 0.5.
How?
From the graph, from this graph,
Okay.
this is sigmoid function at x equals to 0. This is half. This point is
Mm-hmm.
0.5, right? This is 0.5.
Yeah, got it.
So when it is, we usually assume that if this is greater than 0, 1 second, if x is greater than 0, I need some more space. If x is greater than 0, for x greater than 0, we assume it to be p equals to 1, and at x less than 0, p is equal to 0. X less than 0. We assume this is not how it happens. You have to remember that this function over here is
And
basically
WTX and 1 by what does that mean? WTX and this, can you please say it?
W
WTX
transpose
is
X. W transpose. So when you transpose a vector, when when you get a vector, you're given a vector, right? It is given in vertical form. So when you W transpose, your W transpose is this, equals to W naught.
it will be in
W,
horizontal way, is it?
sorry.
It will be in horizontal way, right?
Yeah, it will turn into horizontal vector from vertical vector. Now
Mhm.
W t times x is W naught, W1, W2. So if you remember from the vector multiplication of from vector multiplication, that number of columns of the first vector, should be equal to the number of rows in the second vector. So how many columns does W transpose vector has? 3. And number of columns, number of rows that second X vector has is
Second
3.
X vector.
So
3, yes.
W transpose X can be calculated, and it is nothing but this expression.
Okay.
Yeah. So that is how we start with neural networks. So basically,
Okay.
now the question is, what are the options for the question that comes is, can we use other methods also? So a lot of times, yes. A lot of times, what I tell you from this picture is that you have threshold function, you have ReLU function, you have sigmoid function, you have hyperbolic tangent function, and there is soft plus function also. Soft plus function is a smooth version of rectifier function, and its equation is not given here, but but we can search it, we can find it on Wikipedia. But below is an illustrative image showing how multiple activation functions are used in a neural network. Here one is hidden layer and one is output layer. So all of the X is being passed to all of these units, hidden layer. Now in hidden layer, people prefer to use ReLU.
Value.
ReLU, ReLU. This is
ReLU means which one?
rectifier.
Okay. Rectifier reverse.
Rectified linear unit.
Okay.
And in the output, people prefer to use a research paper that rectifier function gives a better performing neural network than one using sigmoid or hyperbolic tangent. So this paper is there. A research paper proposes that when we use rectifier function for hidden nodes and hyperbolic the sigmoid for the output node, we get a better performing neural networks, and that research paper is linked to that research paper is also given over here. So you can go through it if whenever you have time. And over here, I'm just making a statement giving you the gist of that paper is that a rectifier function gives a better performing neural network than one using sigmoid or hyperbolic tangent. So this was about activation.
What is this graph? Yeah, soft plus and rectifier. And I wanted to understand in which situation we will be using the different neural network. That sigmoid, then hyperbolic means under which situation we will be using the different.
So as a rule of thumb, there are various types of neural networks, but in simple neural network, like if you go by the scikit-learn definition of neural network, scikit-learn implementation of neural network, it was called multi-layer perceptron MLP. Perceptron. In Wikipedia, multi-layer perceptron is a fully connected class of feed-forward artificial neural network, and it is also given in its implementation is given in scikit-learn if you MLP classifier. Okay.
Classifier means it is a kind of a model, is it?
Classifier meaning it will predict it will use for classification. I think there is regressor also. Regressor is not shown over here, but neural networks can be used for regression also.
Oh, okay. So both your it will be used for regression as well as for your classification.
Yes, it can be used for both the purposes. Now, if we are done with this...
Hey, Ashish, can you please give me 5 minutes?
Yeah, sure.
We are done with the session.
You can...
Today.
So yeah, just give me 5 minutes. Let me walk you through a slide. Oh, and then we are done. Like, let's get over it by 12 and connect later if you want. Like, this is the same thing that I was showing you. You saw it that x1 and weight 1 goes to over here, then they're summed up, and then there is step function, and you get this. This is what perceptron is. This is in what do you call neuron in human brain? We call perceptron in artificial neural network. So I think that we can, if you want, we can close with that and continue